Hello, I was passing by your planet and thought, hey, why not do a video on derivatives of natural logarithm functions? I've been making these videos following the order of James Strong's calculus textbook in which edition is it? It's the 6th edition. Now, newer editions and I think some other versions of his textbook don't necessarily have this section quite the same way, but it's something you need to know about in calculus. How do you find the derivative of, say, a natural logarithm? And now, drum roll, please. Ta-da! So the derivative of a natural logarithm is 1 over x. Derivative of the natural logarithm of x is 1 over x. This is what you need to know. This is the most important thing in this video. Have a brain moment and seal it upon thy brain. But anyway, there is a proof in the book. It's a pretty easy proof. So let's go ahead and call y equals the natural logarithm of x. Okay, great. Got that, right? So if that's true, then e to the y equals x, because from previous videos I've done in this section of Strong, it's e and the natural logarithm are kind of like, anybody ever done that string thing where you do the string and then you put your hand in it and poof, your hand's outside of the string? How did that happen? The natural logarithm and e are kind of like that. E to the natural logarithm of something, or the natural logarithm of e to the something, it disappears and you're left with the something. So e to the natural logarithm of x is x. Pull the string and e and the natural logarithm have disappeared and you're just left with x. So we know this is true if y equals the natural logarithm of x. Well, okay, so let's go ahead and take the derivative of both sides. Implicit differentiation. We take the derivative of both sides. And so the derivative of e to the y is e to the y, dy dx. This is, again, part of earlier videos I've done on this section. Meanwhile, the derivative with respect to x of x is 1. Okay, so we've got this. Divide both sides by e to the y, and we have that the derivative of y, that is the derivative of the natural log of x, equals 1 over e to the y, because we've divided both sides by e to the y. And what was e to the y? Well, it was x, so equals 1 over x. There, simply quoterat demonstrandum, QED. We have demonstrated that the derivative of the natural logarithm of x is 1 over x. Okay, well, in general, we can get complicated things that we're taking or more complicated things that we're taking the natural logarithm of. Let's call them u, where u represents bleh. U could be the square root of x squared plus 1, or whatever. U is like a bottle in which there's this algebraic genie. We've shoved in all these things, x squared plus 2x plus 1, whatever. Whatever it is, u represents stuff. If in that case, the derivative of the natural logarithm of stuff is going to be 1 over the stuff plus the derivative of the stuff. And so this is basically the same thing we just had, except we're taking into account that u might be a little bit more complex than just an x. U might be a bunch of stuff, and there are examples in the book. So the derivative of the natural logarithm of u is 1 over u times the derivative of u. Okay, yay. So this, again, that's what you need to know. This is what you need to know. But for a little bit of an explanation or proof, when y equals the natural logarithm of u, where u is a function of some sort, stuff, then we know from the chain rule that dy du times du dx equals dy dx. It's kind of like canceling stuff out in simple algebra. Remember back in the 8th grade or 7th grade when you learned this stuff? This is easy. It can't, du, they cancel out, and you're left with dy dx. So, however, we know that dy du from the previous slide, we know that dy du is 1 over u. And then, so there we have it, the simple proof, or at least it makes sense. Okay, so another way to put this is that if u is a function of some kind, then the derivative of the natural logarithm of that function is going to equal the derivative of the function over divided by the function. This is the same thing. How is it the same thing? Well, because g prime of x is du dx. If u is, remember, u is the function. And so du dx is the derivative of the function, right? It's g prime of x, or the derivative of the function. And then 1 over u is 1 over the function, right? So this is a general way of saying this principle at the top as well. Okay, works for negative x's as well. So that we can say that no matter whether x is positive or negative, this holds. We can say that the derivative of the natural logarithm of the absolute value of x is going to be 1 over x. It's not just for positive x's. And the reason this is the case is because if you have a negative x that you're taking the natural logarithm of, just to flip back to this screen, if you're taking a negative, so it's going to be 1 over negative u times the derivative of u. Well, what is the derivative of negative x? Well, it's negative 1. So the negative that you get from 1 over negative x times the negative that you get from the derivative, the two negatives cancel out. And so for that reason, we can say that whether x is positive or negative, it's going to end up as 1 over x, because if x is negative, the negatives are going to cancel out when you do that little chain rule shebang. Okay, so the corresponding integral using the fundamental theorem of calculus basically says that if I want to, I can go, so the derivative goes this way, the integral goes this way. So if I take the integral of 1 over x dx, it's going to equal the natural logarithm of the absolute value of x plus some constant. Okay, so this is interchangeable. Yay, calculus is fun. It's out of this world. Okay, so just for more fun, I mean, you thought this was already fun. The fun will never end. Okay, so let's use some of the things that we've learned to figure out what the integral of the tangent of x dx might be. Okay, so tangent of x is the same as the sine of x over the cosine of x. So we've just taken tangent, and we've broken it down into sine over cosine. Okay, great. So let's go ahead. Now here's the tricky switch. This is the tricky step. We're going to let cosine of x be u. So the derivative of the cosine of x is the negative sine of x. So if cosine of x is u, then sine of x is negative du dx. And so the dx's cancel out, and we're left with the integral of negative du over u. And we know from our previous slides that that is simply the negative of the natural log of u plus a constant. Because remember, the derivative of the natural log is 1 over u. And so we can pull it out of the integral, and we've got the natural log of u, and then the negative carries out plus a constant. Okay, now what was u? We made cosine of x be u. So we can go ahead and substitute the cosine of x back in, and we've got that the integral of the tangent of x dx equals the negative natural logarithm of the absolute value of the cosine of x plus a constant. But remember, the rules of logarithms is the negative natural logarithm of something is the same as that thing to the negative 1 power, which means you put it in the denominator. So secant x is 1 over the cosine of x. So if I suck that negative back in, it becomes the natural logarithm of 1 over the cosine of x, which is the secant of x. So thus, quoterat demonstrandum, the integral of the tangent of x dx equals the natural logarithm of the absolute value of secant x plus a constant. And I've decided to divide this section up. One of the things I don't like about Strong is his sections go on and on and on. So I've divided this section into 3 videos. This is the first.